Welcome back to your physics teacher. Today we're looking at section 2.2 from the Nelson textbook, and I'm going to be showing you how we can add vectors in 2 dimensions by using components. For question number 4, it asks, what is the total displacement for a boat that sails 200 meters south, 25 degrees west, and then tacks, which means changes course, and sails 150 meters north, 30 degrees east. So good strategy whenever you're drawing the vectors. In this case, first set up a small coordinate system, and then from this small coordinate system draw your first displacement vector, and the first displacement vector is set from south 25 degrees towards west. So from south 25 degrees west. And then we can label this as our first displacement vector, which we can use delta d1. So here delta d1 is 200 meters south, 25 degrees west. Our second displacement then, once it changes course, is 150 meters. But because we're doing vector addition in this case, we have to attach them head to tail. Or another way to think about it is from where it left off, it changes direction from that point. So from the point that we left off in the first displacement, the second displacement is going to be north 30 degrees east. And the pink one here is our second displacement. So our second displacement is 150 meters north, 30 degrees east. And whenever you want to find the total displacement, it just means the sum of the previous 2 displacements. And by doing vector addition is from the tail of the first to the head of the second. So that's a total displacement vector. But now what I'm trying to show you in this lesson is whenever you want to add more than one vector together, you can just think of adding them component-wise. So what that means is to find the total displacement, you do it by the x component separately from the y component. So first of all, our total displacement, like we said, is just the sum of the individual displacements, so delta d1 plus delta d2. And one way of doing vector addition is component-wise, so we're going to resolve or break down the vector along its components. So we're going to have an equation along the x component, and this one picks up all of the x component vectors. And then we have a y component, and this just picks up all of the y components. Right, because each vector can be broken down along its components, and those components are vectors themselves. That's why I put the vector signs. So now all we have to do is just break down each of the vectors that we have along the x and along the y. And in a previous video, I showed you that the easiest way to do this is to remember that cosine is for the x component and y is for the sine component if the angle is closest to the x-axis. So in this case, we're going to redraw our vectors again, and this time we want to make sure that we locate the angle that is closest to the x-axis for them. So the first one, it was 25 degrees closest to the y-axis. So that means we have to find 90 minus 25, which is 65 degrees. And this is helpful because now we can find the x component and the y component. And again, if you remember what I just said, if you find the angle closest to the x-axis, the x component is always cosine of the angle, and the y component is the sine of the angle. Okay, so I'm just setting them up so that way I can put into the calculator. It'd be a lot easier. 200 cos 65, 84.5, 181.3. What were the units? Meters? Yeah. So that was our first displacement vector. We're going to repeat the process. We're going to redraw our second displacement vector, find the x components and y components by first making sure that we're using the angle closest to the x-axis. So initially they gave us 30 degrees, so they really want us to work. So this means that the angle closest to the x-axis is going to be 60 degrees. So this is delta d to x, delta d to y. And again, we're changing it closest to the x-axis because that's easier to connect. This, the x component is going to be with the cosine, and the y component is going to be the sine portion. So it's kind of like a hack. Okay, now let's calculate both of these. 75 and 130. All right, so you see the strategy so far. Whenever you want to add more than one vector, in this case adding two displacements to get a total displacement, we can just treat it component-wise. So use all of the components of x separately from all the components of y separately. So that means that we have to take our two vectors that we're starting with, and we're going to try to find the x components and the y components of each one. But in order to make our life easier, we want to find the angles always closest to the x-axis. Because if we do that, the x component is always going to be cosine of the angle. And the y component will be sine of the angle. So once we have the components, we have to go back to our original equations and put in the values. Now, unfortunately, it is not as straightforward as that, because we're dealing with vectors, and with vectors you have to consider direction. So this means that although we found the values, we have to consider in which direction they point, because based on that, we're going to associate it with a positive sign or a negative sign. So there's a lot of steps involved. So for the displacement 1x, notice that the vector was pointing to the left, so we have to put a negative sign for it. And our second displacement along the x was actually pointing to the right, so we're going to put a positive sign. And then we put in the values that we found, so negative 84.5 plus 75. Which is negative 9.5. For our components along the y, our first displacement vector along the y was pointing down, so we have to put a negative. And our second displacement vector along the y was pointing up, so we have to put a plus. So this means we have negative 181.3 plus 130, which gives us negative 51.3. Okay, so I just made this small, so it was getting in the way. So you see, once you have our total displacement along the x, and we have our total displacement along the y, we have the pieces of the vector itself. So we're going to try to put those pieces back together. So the x part, since it's negative, it points to the left. And the y component was negative, so it's pointing down. And then our total displacement, we can just now connect it. So you see, once we have the x and the y components, we have to reconstruct the original vector, because now we have the two pieces of it. And because we're looking for a vector quantity, that means that we're going to find the magnitude and the direction. So to find the direction, let's call this angle theta. So from this angle, we can call this side opposite and this side adjacent. So remember, to find the angle, the best thing to do is always use tan ratio. Tan theta, which will be the y component over the x component. Okay, so shift tan, 51.3 divided by 9.5. It's about about 80 degrees. And now we want to use Pythagoras to find the hypotenuse, so we're going to use CAB. So delta D total is just the square root of the sides squared and added together. So that's 52.2. meters, was it? Yes. Okay, so see, we had to find the magnitude and direction. So our total displacement vector has a magnitude of 52.2 meters, and the direction is going to be west 80 degrees towards south. Okay, I'm going to skip the other one. It's just more repetitive work. Number 7 is a little bit more exciting because here we have to add 3 vectors together. So you're going to see the same strategy that we used before. We're going to use it here as well. So whenever you want to find the total displacement, delta dt is just the sum of the individual displacements. But because now we're dealing with vectors in 2 dimensions, the best thing to do is to add these vectors together. We're going to add them component-wise. So what that means is that we're going to find the x components and add them together, and then find the y components and add them together, and making sure that we consider the directions, right? Okay, so it's actually quite complicated, right? So to add up vectors using components, you write an equation around the x component, so that's separate from the y components, but they are vectors. So right now we have the arrowheads on top. So our mission then is to find each of those individual pieces. But to do that, we need to draw each of these vectors and find the x and y components. The easiest method is to remember cosine is with the x component and sine is with the y component whenever the angle is closest to the x-axis. So whenever we're drawing these vectors, we're going to try to find the angle closest to the x-axis, and that will make our life a lot easier. So the first displacement, north 30 degrees west. So that's 30, then closest to the x-axis would be 60. So this makes our life a lot easier, you'll see. So delta d1x, delta d1 cosine 60, and delta d1y, delta d1 sine 60. And what was delta d1 equal to? It was 25. Now we do have the components, but remember these are vector quantities, so you have to still keep in mind the direction that they were pointing towards. So the x component was pointing to the left and the y component was pointing up. So that's going to be helpful, all right? Okay, our second displacement, this one was north 40 degrees towards east. They always try to make it so hard for you. They never give you the angle closest to the x-axis. Why are they so mean in Nelson? They should just make your life easier once in a while. So this would be 50 degrees. Delta D2 is 30. And remember, now that we found the angle closest to the x-axis, it's straightforward because we can find the x component and the y component very easily. Right? The x component is the cosine part, and the y component is the sine part. But again, it gets annoying because these are vector components and they have directions. So the x component from this diagram points to the right and the y component points up. So that's going to be useful later on. I'm trying to make it small. And then my third displacement, this one is south, 25 degrees west. Again, they're giving you the angle closest to the y-axis. They're just brutal. They're just mean. So this is 65. Delta D3 is 35 meters. And because now we found the angle closest to the x-axis, the x component is the cosine of the angle and the y component is the sine of the angle. They're just mean. They didn't give you the single one closest to the x-axis. This is 15. That's 32. And again, they have directions. The x from this diagram appears to point to the left, and the y points down. So now the reason why all of that was important is because when we put it back into our equation, we have to keep in mind the directions. So delta d1x was negative, delta d2x is positive, delta d3x negative, right? Depending on the direction that it points. If it points to the left, we take it as negative. If it points to the right, we take it as positive. For the y components, delta d1y pointed up, so it's positive. Delta d2y points up, so it's positive, and delta d3y points down, so it's negative. Okay, so now at this point we already have the negative and the positive, so we just have to put in the values that we calculated before. Gia, stop. So from this, it appears that the total displacement, the x part points to the left, and the y part points up. So the whole reason why we found the components is that now we want to reconstruct it. So the x component points to the left, and the y component points up. So our total displacement is that one there. Okay, there. So this had a value of 8.2. This was 12.7. Now the reason why I did that is we want to find the magnitude with the Pythagoras theorem and the direction from the tan ratio. So we done that before, right? So tan theta will be opposite over adjacent, which is the y component, over the x component. Tan inverse of 12.7 over 8.2. So this is 57 degrees. And then to find the magnitude of the length of the vector, you're going to use Pythagoras. So c squared equals to a squared plus b squared, because we have a right angle triangle. Right, because x and y components would always be perpendicular to one another. So this is the square root of the sum of the square root of the sides. So that's 15 meters. So this means that our total displacement, it's a vector quantity, and the magnitude is 15 meters, and the direction from this angle that we found is west 57 degrees towards north. Keep in mind that you might have found the angle to be different, but maybe you found it north going towards west. So that means you should have gotten an angle of 33 degrees. So both are correct, depends on how you report the final answer. So that was it for this lesson. I know it was probably the hardest one so far in the course, so make sure you watch it slowly and then ask me any questions, all right? I'll see you in the next one.